Welcome to this video on electromagnetic induction. In this video we're going to look into the idea of magnetic flux. But before we get there, let's first imagine you have a fan. So this is a fan, and this fan is blowing air, and you have a window here, and we want to find at what is the flow rate of the air that flows through the window, right? So this blower is going to blow air, and we want to find out what is the rate at which volume flow rate of the air. So we want to find the volume of air flowing through window. To do that, we need to know the velocity of air passing through the window. So let's assume that at this position 1, the velocity of air is V1. So the volume of air flowing through the window would be V1 into the cross-sectional area. I mean, you can try to put the dimensions here, and you will get it as meter cube per second, which is for your volume flowing through the window, right? Now, the volume flow rate at that position of the fan is V1 is given by V1A. Now, as you bring this fan closer, so imagine that you bring this fan closer. As you bring this fan closer, what you will observe is that the wind is blowing in a much faster rate because you brought the fan closer. And this velocity of this wind here would be V2. So your volume flowing through the second position would be equal to V2 into A. And let's assume that this is time T1 and this is time T2 in this position 2. So the difference in the change in the volume flow rate, the change in volume flow is equal to delta V, that's V2 minus V1, and the rate of change of volume flow would be delta V by let's say the rate of change in volume flow would be given by delta V by delta T, and delta T is nothing but T2 minus T1. So this is a rate of change in the volume flow. So you can say that, let's say at this position the volume flow was 10 meter cube per second. That's a lot of air, and here it is 20 meter cube per second, and the time was in 2 seconds. So your rate of change of volume would be 20 minus 10 divided by delta T, which is 2 seconds. So 2 seconds. This is seconds. Looks like 5. Sorry. So that's you will get it as 10 by 2, and this is of course meter cube per second. So you get it as 10 by 2, that's equal to 5. So you get the rate of change of volume flow would be 5 meter cube per second every second. So that's what it means. Every second your volume is increasing by 5 meter cube per second. That's what it means, rate of change of volume flow. Now, exactly the same way, you can imagine that you have a magnet and you have a window. Or instead of window, you can imagine that this is, in this context, this is a coil. And as you keep this magnet here, there is a certain amount of magnetic field lines that cuts across this window or coil, right? And we say the magnetic flux, we call it magnetic flux, and it is denoted by phi. It is read as phi. It's a Greek symbol, is given by the B into the area. So corresponding to this position, there is a magnetic field strength due to that magnet being there, at this position in the coil. Let's say this is B1. So you have B1 into area, and area is a cross-sectional area of this whole coil. So let's say this is phi 1 because it's at position 1. And as you bring this magnet close, you will observe that the flux is increasing because the magnetic field strength increases. So your phi 2 will be equal to B2 into A, where B2 would be the magnetic field strength at this point. So that's your flux. And the changing flux, the change in flux is denoted by delta phi, and that is equal to phi 2 minus phi 1. The same as the volume flow rate, right? And if let's assume that this change happened between time t1 and t2, we know that this change happened in delta t is t2 minus t1. So we say rate of change of flux is equal to delta phi by delta t. Of course, your phi unit of phi is Tesla meter square. So we say it's Tesla meter square divided by delta t seconds. So this represents rate of change of flux. As you bring the magnet closer to this coil, we know that the rate of the rate of change of flux would be positive. As you take this magnet away, then the flux lines are reducing, so your rate of change of flux will be negative, right? Because your flux lines are reducing as you take it backwards. So we say the flux lines are negative. I hope you got a sense of what magnetic flux is, because in the next video we're going to talk about Faraday's law, and we're going to give the definition from point of view of changing magnetic flux. See you until the next one. Bye.